Hello and welcome to Lesson 5. Lesson 5 is the chain rule. The chain rule. That's for composite functions. Functions of a function, if you remember correctly. Quick review of that. F composite g of x is equal to f of g of x. Right? The function of a function. Instead of inputting 2, I might, to get it into function f, let's say if f of x equaled x squared and g of x equaled 1 over x, if I inputted a 2, this would be 2 squared. But if I input g, then this would be whatever g is squared. Does that make sense? All right. So when I'm doing a derivative of something like that, I either have to do the function and evaluate it out, which we could do. I probably won't belabor that on this one. I want to do more examples. But just like we did in the past, we could do the function of the function, right? If I did this function of this function, it would be 1 squared over x squared. That would be f composite g of x in this case. Then I could do its derivative, right, by flipping it up. I could use the product rule, right? So I could show that just as easily. And maybe we'll do that as the first one. We'll see. However, let's go back and look at this, and let me give you the rule. So now, when I write it this way, it's not as evident. But when I write it this way, there's clearly an inside and an outside. Okay? So with the power rule, we just had one monomial to do at a time. With the product rule, we had a first and then a second. Okay? And with the quotient rule, we had a top and a bottom. Now, we have an in and an out. All right? First, second, top, bottom, inside, outside. So the rule is the derivative of the outside, the derivative of the outside with respect to the inside times the derivative of the inside. So the derivative of the outside with respect to the inside times the derivative of the inside. All right? And there's no really good shorthand way. I put derivative of the derivative of the out with respect to the in times derivative of the in. I mean, doidy, I don't know. However you want to do it, I just think in this case it's easier with the words. The derivative of the outside with respect to the inside times the derivative of the inside. Okay? So that's what we're looking at. So let's look at one. Let's look at that one we just looked at. We said, what if that was true and that was true? Then we said, look, f composite g of x is g of x inside, and f of x, which was the square, whatever the input is the outside function. Does that make sense? So let's look at that function in its simplest form and see it. Okay? So what I have is the derivative of the outside. Okay? So the derivative of the outside is this squared function. So the derivative of the outside is this squared function. So that's 2 times whatever that was being squared to the 2 minus 1, or the 1. So it's just basically the power rule. Right? But what was in there? What was in there was g, and I don't change g. I just did the derivative of f, and I left g alone. Now, I do times the derivative of g. Okay? So, I would have to either do the quotient rule here, or I could flip that x up and make that x to the negative 1. I'm going to do the quotient rule because we haven't done that yet. And I'll show you that it ends up the same way. So the derivative of the top, that's a constant. That's 0. Times the bottom, which is x. Minus the derivative of the bottom, which was x. The derivative of x is 1 times the top. All over the bottom, which is x squared. Yes? So let's simplify that bad boy. This is 0. This is 1. Yeah? So what I get is 2 times 1 over x to the 1, or, right, let's just write it that way again. 2 times 1 over x to the 1 times 0 minus 1, negative 1, over x squared. Look at that. All right? And now I could simplify that further, but that's the derivative of the outside with respect to the inside times the derivative of the inside. Right? And if you think about this, this flipped up. Right? If that flipped up, I'd do negative 2 times 1. Right? So you see how that, or I'm sorry, negative 1 times 1. And 1 minus 1 would be negative 2. Then it'd flip back down. I have negative 1 on top, negative 2 on bottom. Okay? If you don't understand what I just said, I'm thinking about if I would have written 1 over x as x to the negative 1, and then did the power rule, it would be negative 1 times 1, x to the negative 1 minus 1 is negative 2. That negative 2 should have went to the bottom, so it would have been negative 1 on top with x squared on bottom. And now you can see that that truly is what I got there. Okay? So that's the answer, but I'd like it simplified, something like that. This is 2 over x, right, times negative 1 over x squared. What does that simplify to? Negative 2 over x cubed. That's probably what you're going to see in your book, in the back, in the solutions manual, right? But this was the answer, right, in its first step form. So that's, again, where I want you to box it, and then simplify it every now and then to make sure your algebra skills stay crisp. Let's do another one. I said I wasn't going to do that to prove that it worked, but it worked. You saw that it worked. So now that's pretty much telling you that you could do the derivative independently and put them together, or do them separately. So let's do some more. Let's do this. Let's do okay? So what is the inside? What is the outside? And here's what I want you to do. I'm going to ask you to do the derivative of the outside with respect to the in, and the derivative of the inside as two separate things. All right? So you stop and do that. Welcome back. So let's do the derivative of the inside. What is the inside? The inside is that. Okay? So what is the derivative of that? That is 2 times 3, or 6, x to the 1 minus 0. Yes? Bang, that's done. What about the derivative of the out? The derivative of the out is that. So that's something to the 5th power. Therefore, it's 5 times something to the, that's right, 4th power. What goes in there? The n as is. So what is the answer to this problem? It's this first, that second. It's just that simple. I end up taking that times 6x and plugging it in at the end right there, and that is my answer. So it's really not that hard. It's really not that hard. Okay? Now, there comes a time with these composite functions where you're going to get trig functions and e functions and natural log functions and all kinds of other functions that we haven't talked about yet in these videos. But you should have already looked at some of the document camera analysis of those. And I'm going to make a video at the end of all the special functions. So you might need to look at that last special function video, and you might have needed to do it already. But you might need to look at that to get some of these special functions that you need. I'm assuming that you already have, and if you haven't, you might want to stop now and look at them, and then come back to this video afterward. Okay, so now that I think you've done that, let's look at some of these with other functions. So let's do the derivative of c e to the x to the 2. Let me make sure I don't give you something that's too hard for you to do, and I think I am. So let's just make that a 7. Okay? All right. Now, we learned from the previous videos that the derivative of e to the x is e to the x. Okay? That's the truth. So when I do the derivative of the outside, which is 7, right? 7th power. That's the derivative of the outside. With respect to the inside, means whatever was in there goes in there unchanged, times the derivative of the inside, where the derivative of e to the x is e to the x. Okay? So that's the answer, but when I have e to the x to the 6th times e to the x, let's think about, what does it mean when I raise a power to a power? It means that I have that thing 6 times. E to the x times e to the x times e to the x times. So that's e to the 6x. So I have 7e to the 6x times e to the x, which is 7e to the 7x. So when you got these e's, yeah, you know, it's messing with you a little bit, right? But just to establish, if you didn't go back and look, why that's true, and you should have went back to look, I know that the derivative of any constant to a functional power, right, is equal to that statement times the natural log of the base, this is the base, right, times the derivative of that outside part, dx of, in this case, x, right? So when I do the natural log of e, natural log is the inverse function of the e function, and e function is the inverse function of the natural log function. So what happens is when I do, okay, so this was just me thinking, right? That was me thinking about the function, the derivative of a constant raised to an exponential function. Okay? So when I do that, I say, well, okay, the natural log of e, and you can put that in your calculator, all right, times the original statement, e to the x, times the derivative of x. Well, the derivative of x is 1 x to the 0, or 1. And what you'll find when you put the natural log of e into your calculator, you get 1. So what you get is 1 times e to the x. All right? So the derivative of e to the x being e to the x isn't some magical thing that we just said, let's just make it e. It just works out from the general rule with that special base that's the base of its own log. The natural log of any other number won't be 1. Only the natural log of e will be 1. All right? E to the 1 in particular. Okay? So that's just a little something, something there. So let's extend that. Let's go ahead and say, well, we understand that because we've looked back at those lessons. So let's look at this. What is this? Is that a composite function? Do I use product rule, power rule, chain rule? What do I do? Well, e to the 1 is a constant, so I'd use the power rule. E to the x, though, is not a constant. E to the x is an exponential function. And that's a function of a function. So I'd use the composite rule. So e to the 3x plus 2 is a function, an exponential function whose exponent is another function. Can you see? It's chain rule. And the chain can be chain to chain to chain to chain. And we can get really crazy with it. And we'd like to do something in my class when it's not flipped called the chain rule challenge, where my do nows get increasingly more convoluted and we try to solve those. So let's look at this. What is the inside? What is the out? E to the exponent is the outside part. The outside thing is that this is exponential. So this is kind of weird. So the outside is e to the exponential function with the inside as it falls. So you can't say that's always out and that's always in. What's outside is the exponential value. And then what I put into the exponential function was that thing. Instead of being the base, now it's the exponent. So this is the derivative of the outside with respect to the inside. Now the derivative of the inside is the derivative of that statement. The derivative of the inside is the derivative of 3x plus 2, which is 3x to the 0 plus 0, or 3. So the answer to this is 3e to the 3x plus 2. Consequently, any e except e to the single 1x to the 1 power is a composite function. So e to the 2x is equal to this statement as it is, e to the exponent is equal to itself, times the derivative of the exponent, which is the derivative of 2x, which is 2, times the natural log of the base, which is e, natural log of e is 1. So this is 2e to the 2x. Okay? You're starting to see a little pattern? Let's do one more. What is e to the 15x plus 7? Well, e to the exponent is itself, right? Its derivative is itself. So I'm going to write that statement, itself. The natural log of the base e is 1, so 1 times that doesn't change it. And the derivative of the inside is the derivative of that, which is 15x to the 0 plus 0, or 15, which is 15 e to the 15x. Let me write that a little nicer. 15x plus 7. Are you starting to see a little pattern with e's? I hope you are. Okay? I hope you are. All right, now let's go ahead and look at some other ones, some other composites. All right, let's look at the composite of the natural log of 3x plus 2. The natural log is a function. It's a natural log function of some input. The input in this case is 3x plus 2, so this is a function of a function. This is a composite again. And e and natural log are their own inverses, right? So it makes sense if e is a composite, so is natural log, and vice versa. So what I'm going to do is, what is the outside? Well, the outside is the natural log, okay? And the inside is what I'm taking the natural log of. So I'm back to that same looking pattern. It's the e to the power that breaks the rule. It's sort of like the I before e rule. Mostly true, but every now and then e comes first. So let's look at this. The natural log of a function, again, if I go back to those natural logs, right? The derivative of the natural log of x is 1 over x. So in other words, the derivative of the natural log of any function is 1 over that function. Okay? Just that simple. It's a rule. That's all. So now I can prove why that's true, but it's not important for me to do that. This is just something you can memorize and look at on your own so that it makes sense why, that you can remember it in case you forget. So let's do the rule now. Well, if this is a natural log, and that's how I take the derivative of the natural log, that means the derivative of the natural log is 1 over whatever I'm taking the natural log of. In this case, I'm taking the natural log of this function g. F would be this, and g would be that. So it's 1 over 3x plus 2. Then it's times the derivative of the inside. I need to now take the derivative of that. Okay? And when you see this, right, 3x becomes 3 plus 0, right? So what does this become? 3. I can imagine that 3 as a whole number, as a fraction over 1. So this becomes 3 over 3x plus 2. All right? Bing, bang, boom. Not so bad. Let's analyze over here real quickly, in case you didn't go back and look at that lesson like I told you to. I'm anticipating you just doing to push through. So if you didn't, look at this. Again, if I did this 1 over x, that's the derivative of the outside, times the derivative of the inside. The derivative of the inside is the derivative of x, which is 1x to the 1, right? Well, 1x to the 1 becomes 1x to the 0. So what happens is that derivative basically is multiplied by 1 on top every time. Well, what was the derivative here? It was 3, right? What if that derivative would have been 7? Then that would have been 7. You see the way that's looking? Right? So let's do another one. Let's do another one. Wait, let's make it even better. Let's make it 6x squared plus x. So we can really see how that breaks down. So let's go ahead and apply the rule. The rule is the derivative of a log is 1 over whatever I'm taking the log of. I'm taking the log of 6x squared plus 6, or plus x, I should say, times the derivative of what I'm taking the log of, which is 6x squared plus x. So that's going to be times 12x to the 1 plus 1. That's a whole number. I can imagine it over 1, which means top times top, bottom times bottom. I hope you're starting to see the pattern. What I get is 12x plus 1 over 6x squared plus x. No, I'm not going to cancel that way because addition is not undone by a division. But what I am going to notice is the derivative of the inside is on top and the original input was on bottom. That makes it easy. It's this over it under its derivative. That's really what it is. It's this under its derivative. Okay? So it's a really simple rule when I'm using e's and logs, I think. Logs particularly. When I'm using logs, it's Whatever I took the log of is on bottom, and the derivative of that number is on. So it's x over dx. I could think of it this way: it's whatever x is, and its derivative on top of it, dx over x. The derivative of whatever that is over whatever that is. That's really what it is. I only show this to you because later that's going to be a really fundamental understanding when we start talking about integration. Okay? So let's do some more. So let's take the derivative with respect to x of the natural log of e to the x to the fourth minus 3x plus 2. Okay? Starting to get crazy. Like, holy crap, what's going on? I've got a natural log, I've got an e, and I've got a polynomial. I've got a bunch of stuff that I've been dealing with independently. Now they're all meshed together. All right? The composite rule is the rule, right? It's the one that lets you do everything. Or the chain rule, I should say, is the rule. It's the one that lets you do everything. So, first of all, let's think about this. Which one is the outside? Hopefully you're looking at it and this is outside, right? So the outside is the natural log, isn't it? Well, which one's the inside then? So the inside is what's in there, right? And this inside is e to the x to the fourth minus 3x plus 2, right? But e to a function is another function. So what I have is this in is the other out, right? In other words, e to this power is the out, and the new in, or the second in, I should say, is the exponential function. So can you see how I could have nested? I could have dozens of these. Out of an in, which is another out that has its own in, which is another out that has its own in. I could, like Russian nesting dolls, I could have dozens of those composite functions in there. I'm just going to do a couple of these 3 ones and stop. So how do I do this? Well, I do it just like I wrote it. I do the derivative of the outside with respect to the inside, then the derivative of the inside. But it's an outside of its own, so after I do it, I've got to do the derivative of the new inside. If it was an outside of its own, I'd have to do the derivative of the new inside. So it's derivative, 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 derivative to the last inside, and then it's done. So let's look at it together. So the derivative of log is 1 over, right? And what am I taking the log of? That's what goes on bottom. That's the derivative of the outside. Okay? Times the derivative of the inside. This is the inside. Its derivative, the derivative of e to the oomph is e to the oomph, right? So underneath here I write e to the oomph, and oomph is x to the fourth, because I've got to do it with respect to its own inside, right? And now finally, that e to the oomph, I have to do d oomph, right? The derivative of that, and that's going to be 4x to the third minus 3. Okay? So when you look at this, that is the answer. However, it should be remarkably obvious to you that this is a fraction. So if I made this a fraction and this a fraction, I could combine them all together with multiplication of fractions algorithm. The top 1 times that, e to the x to the fourth minus 3x plus 2, times that, which is 4x cubed minus 3. That's all the top. And 1 times 1 times 1 is on bottom. That's e to the x to the fourth minus 3x plus 2. Something jumping out? Should. This is times and divided. Well, those are inverse operations, and this is something over itself. What is my answer really? My answer really is 4x to the third minus 3. Why did that happen? Because natural log is the inverse operation of e. And when I do that, I see the inverse operators end up being something over themselves, right? The function over its derivative cancels because of that special e relationship. So when you're dealing with e's, you got to watch it. Okay? You got to watch it. Let's do one more. Let's do the derivative of the sine of the cosine of e to the x. Okay? Now, again, you should have looked back and saw the derivatives of sines and cosines, tangents, cotangents, secants, and cosecants. I'm going to keep it simple because if you haven't done that, I want you to go back and look at it because I derived those trig functions particularly. But I can tell you this. We learned that the derivative of sine was cosine of x, and that the derivative of cosine is negative sine of x. That's what we learned. And we'll look at that in the other video, or you will. I'm not going to belabor it more here because this is already 30 minutes long. So what I'm saying is I can do this now with those two rules that you should have researched on the other time. Okay? So let's do it. What's the out? What's the outside? Well, let's do this. This is out 1, and this is in 1, right? But inside 1, we have, basically, inside 1 is outside 2, right? And outside 2 has its own inside 2, right? And in theory, inside 2 is outside 3, and that's inside 4. But we know e to the x. If I'd have made that 2x, I'd have had, let's do that. Let's make that 2x. Now, I have to say, oh, inside 2 is actually equal to outside 3, and this is inside 3. So I'm going to do the derivative of that with that inside of it, then the derivative of that inside thing with that inside of it, and the derivative of that inside thing with that inside of it, and the derivative of that thing last. That's how it's going to go. That's how it always goes. You can do it this way, you can do it that way, you can line it up and then organize it, but you've got to keep track of it. All right? So the derivative of sine is what? Cosine. So the outside one is first is cosine. Cosine of what? It's the cosine of all that crap as it is. And I'm going to write all that in black before, since it's not changing yet. Okay? That's the derivative of the outside with respect to the inside. Okay? Now I need to do the derivative of the inside. So I'm going to use a different color for that. The derivative of the inside is cosine. What's the derivative of cosine? It's negative sine. So it's times negative sine of, right? Of what? Of the inside part, which is e to the 2x, right? Okay? And I'm saying, okay, so I've done the derivative of the outside with respect to the inside.